this is the last videos of this series of videos with almost no math, Well, to be honest, with this one, to understand the mysteries of theory of relativity and also why they are not actually mysteries, you do have to use mathematics, okay? So I made another series of videos, to really understand the details. But here, we'll try to explain, the major steps in the line of thoughts to understand those mysteries, which are not mysteries. It is crazy. Okay, so first of all, we have to realize that relativity actually makes sense, as opposed to quantum physics, which is really not natural and sounds crazy sometimes. With relativity, if you really follow in details, if you actually define everything, with precision, then it actually makes sense, okay? But the problem is there are non-obvious implications, about space and about time, as we will see and as you probably already know. And also it's subject to misinterpretations, I remember, there are a lot of misconception when you look, for instance, at the twins paradox and talk about, it's because there is acceleration or deceleration. No, it has nothing to do with that. So we'll go into those details in a few minutes. Now, in fact, there's not one but three theories of relativity, okay? There is the relativity from Galileo, so 17th century or something like that. And then there is Einstein, special and general relativities. So let's have a look first at the Galilean relativity. What it says is that the same physical rules apply for all Galilean frames of reference. And that there is no privileged Galilean frame of reference. Whatever happens in one Galilean frame of reference can happen in any other one. There will be the same rules. But the question is, what is a Galilean frame of reference? Well, it's fairly easy, actually. Here is an example here of a car moving, at a constant linear speed. And there's no acceleration. You don't feel anything. Actually, if you do measurements, you will see the same thing as if the car was just stopped here, which is what you would see also from a fixed ground like this, And so these are, both the ground here and the car, the moving car in a linear way here will both be Galilean frames of reference. So, and actually Galileo didn't take that as an example. He took a boat because at that time trains didn't exist. Okay. Now let's assume we have a man, walking in a car like this at 10 kilometers per hour. Okay, so relative to this car, we say the man has a speed of 10 kilometers per hour. Now, what happens when you look at this man, walking like this from the ground here, with this car moving here? What happens is that, okay, the speed of the man, relative to the car is 10 kilometers per hour, but if we consider that the car here is moving in 100 kilometers per hour relative to Earth, relative to the ground here, then in order to see the speed of the man here relative to Earth, we just have to add the two speeds, piece of cake. So this will be 110 kilometers per hour. Yeah, okay. But the problem, arrives when you place a man by a light ray like this, Then all of a sudden we see a problem. And Galileo didn't see that because he didn't have the tools to see that. But in fact, what happened is when you measure very precisely the speed of light, from inside the car, you will find, a definite number like this, okay? Roughly 300,000 kilometers per second, sorry. That's crazy. Okay, so there's the speed of light relative to the car is equal to that number. And then if the car itself is moving relative to Earth, again at 100 kilometers per hour, then what you might think is, well, then the light ray here, viewed from Earth, will have a speed of that, 300,000 kilometers per second plus 100 kilometers per hour, But in fact, if you measure with really, really good precision, you will actually find the same number. Just as if the car was not moving, and that was a big problem, for physicists for quite a while, and it was really, really bad because, all of a sudden you said, well, Galilean relativity made sense, we just add the speeds, but when you look at the constant speed of light, viewed from Earth and from the car, then these two theories are incompatible. There's something wrong somewhere. And everybody was confused about that, And then comes Albert Einstein. And he said, well, wait. I'm going to explain to you. He said, okay, well, first you have to define precisely what you're talking about. We have to define time. Time is, okay, it seems obvious, but let's try to see how we can define time, how we measure time, for instance. And he said, for that, we need to define what's called simultaneity, okay? And then we'll use clocks, and then we'll be able to measure time, So the way he did it, he said, well, let's assume here we have, one lightning here and one lightning there, striking those mirrors here. And, well, when that happens, if we see from here, the middle point here, if we see both lightnings arriving at the same time, or in other words, if I see only one lightning, instead of two, then that means that the two space-time events here will be simultaneous by definition. That will be my definition of simultaneity. And everybody said, yeah, okay, that makes sense. Yeah, okay, we agree. Say, okay, you sure? Yeah, sure, we agree. Okay. But then it had some implication. Because now if we look, at a moving frame of reference like this relative to another frame of reference, again, Galilean frame of reference, what happened is that viewed from the car, from inside the car, those two simultaneous events, viewed from Earth, will not be simultaneous anymore because this lightning will arrive sooner, will arrive first because the car has moved this way. And then the second one will arrive. So they will not be simultaneous viewed by the car. So what that means that simultaneity depends on the frame of reference. So if you want to define time from there, that means, time is not absolute anymore. It depends on the frame of reference. Wow. Okay. Now, thanks to the new definition of time and space, that we've seen in previous video, and also the concept of simultaneity, we can show, like Einstein, that for two Galilean frames of reference, clocks do not tick at the same rate. Yeah, but we need math to do that, okay? Sync clocks do not display the same time, and lengths of objects are not the same, depending from where you measure them. And all of this, again, is proven in some other videos that I made. I put the link in the description, of this video. Now let's take an example, and again, this is really explaining details in another series of videos. Again, I'll show you the links. It's called the twins paradox. You have two twins, so they have the same age. Twins, okay? So, and one of them, let's say the sister here, takes a rocket, which goes very fast, really fast, and for quite a long time, several years. And when she comes back, what happens is that they compare, their age, and the sister here, the twin sister, is now younger than the twin boy here, the twin brother. And so, this was weird. But that, we can prove that from the definition of simultaneity that Einstein gave us. And that means there's one paradox, where the traveler twins is younger than the Earth twin, they don't have the same age, But then there's another paradox, because relativity says you can take any frame of reference you want. So we could take, in theory, we could take the frame of reference from the sister here and assume that it is the brother with the Earth moving away from the rocket and the sister. And we have the right to do that, in physics. But then the implication would be, if we use the same rules, that we showed to prove this, then it would be the boy who would be younger than the sister. The brother would be younger than the sister. So that's the second paradox. Okay, but in fact, you cannot use the sister's frame of reference because it's not Galilean. Because when she leaves Earth, well, there is some acceleration, and therefore, by definition, it's not Galilean. So you have to use, to compare the clocks, you have to use the brother's frame of reference. Okay, and that's why you can explain that. So this can be explained by the mathematics, and this can be explained by the fact that, you have to use Galilean frames of reference in special relativity. There's not one, as a summary, there's not one but two twins paradoxes. In fact, they are not paradoxes, and you just need to apply the special relativity formulas. For example, when you want to add the speed, well, instead of a simple addition like this, like in Galilean relativity, well, you'll have to use a little bit more complex equation. Therefore, you don't need, acceleration, deceleration, as I've seen in many videos. We don't care about that. And also, that will imply that there's no absolute space anymore. There's no absolute time anymore. And that means that, everyone or every object has its own frame of reference. Yeah, as soon as it's moving, So when you say at the same time or at the same place, it has absolutely no meaning if you're not in the same frame of reference. Okay? Okay. Another derivation from special relativity rules and math that I will also show in the videos is, well, energy is equivalent to mass, or mass is equivalent to energy. But I won't go into more details here. And also, okay, there is one last interesting point here. And I promised I would talk about it, so I will here. It's called the non-local causality problem. There is an experiment imagined by John Bell, an Irish guy, an Irish physicist. And he, what happened is that you have, for instance, two photons which are generated, together, and then they using mirrors, etc. They split, and so one goes 1,000,000 miles away in this direction, and the other one goes 1,000,000 miles away in the other direction. And what happens is that something happens to this first photon here, and at the same time, it will happen something equivalent on the other photon here, there. That's 2,000,000 miles apart. That's crazy, and it's been proven. I mean, it's experimentally proven, and of course, the theory says so as well. And so, that's kind of a problem because Einstein told us, well, information cannot go faster than speed of light, and so if something happens to this photon, it has to somewhat tell it to the other photon there, but it should take, a while to get there because, you cannot be faster than the speed of light. But in fact, it happened at the same time, simultaneously, more precisely. And that's a real big question. And one way to think about it is that the photons actually, in the photons frame of reference, time is fixed, and time and space in their frame of reference will only change when you measure the photon's positions, Yeah. And therefore, while from our frame of reference, we see photons coming from the source, and then we see them a while later in our frame of reference, in our space-time frame of reference. We see them later, some time after that, we see them having the same behavior. Well, in fact, in the frame of reference of the photons, nothing happened. They were still in the same time, in the same position. So if something happened to one of them, it happens also to the other one. That's crazy, right? Yeah. So that's the idea. It's not a proof, but it gives you maybe a clue of what's going on for non-local causality. Now, let's talk about general relativity. Okay, all of this now was about Galilean frames of reference. But now we have to be more generic, and that's what Einstein said. We need to generalize what we saw about special relativity. Everything is the same for all frames of reference, provided they are Galilean, no acceleration. But he said, okay, now it's time, to consider also other frames of reference, which do have some acceleration, where you can, feel the acceleration. And that will be called the general relativity. And you probably heard something like, well, what happened is that mass energy curves space-time. And what the heck does this mean? And that's what we're going to explain in this video. Well, sort of. To prove it and understand why, we need two things. We need the thrifty universe principle. TUP, you remember the first videos? Well, if you didn't watch them, you better watch them now, okay? And because this is really the principle from which you can derive this. Yeah. And the second thing is you need, the mathematical world object called tensor. Tensors are very powerful, as we'll see. Now, the TUP, says something like, when changes occur around an object or particle, the universe will adapt it to optimize the changes. Again, if you want more details, just go look at previous videos, and I have also a series of videos which goes in detail, on the mathematical side. But basically, you have the example of a ball, on the Earth here, and so the ball can go up and down. So you have some kinetic energy here, some speed, and it will go, at a certain speed, and then because of the gravity on the other side, which acts as potential energy, the universe rule will say that the kinetic energy must compensate for that. And so, but, in a very optimized way. So it will go slower, 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 and then we'll have to go negative, and faster, faster, faster in this direction. And that's because of TUP. Yeah. Okay, tensors now. Tensors are math objects with three important characteristics, very key. First of all, they represent many different objects. They can represent numbers, vectors, and even functions. So it's a very powerful way of writing things in the mathematical world. The second thing is that they supposedly simplify equations. At least, equation looks simple when you see them written as tensors. But in fact, tensors can be very complex objects, and therefore they hide the complexity. But as we'll see, it really helps. And finally, one of the key points with tensors is that they are valid in all frames of reference, including non-Galilean frames of reference. In other words, when you have an equation that works in any frame of reference, it will work in any other frame of reference everywhere in the universe. And that's fantastic, because that's exactly what we want for general relativity, find rules that will work for all frames of reference, okay? And so tensors are great for that. So, let's see. Let's look at the first sentence here, represent many different objects. Well, for instance, X. A number is a tensor, and this number can be a real number, it can be an integer, or it can be a complex number, if you know what that means. But it can also be a vector, so a vector is also a tensor. And it can be a matrix like this, which can represent fairly complex functions, of which can be applied to vectors or on other functions. Because, this is really a very powerful math tool. Now, as an example, when I said the simplified equations, Well, for instance, something like this can be written as a tensor like that, you know. So this is simpler than this. So you can, use this form, to play on equations and do multiplications and additions, and whatever. And at the end, once you have finished and you have your final equation, well, you replace the tensor name here with its actual value, and then you do all the calculations. Usually you use a computer because there are so many calculations to do that it's quite tedious. So so the simplified equations, because again, you can write it very simply here, but also they have very simple rules. When you do addition and a special tensor product here, for instance, in an addition like this, where the two tensors here have the same indices. As you can see in a tensor, you can have multiple indices, as opposed to a vector, or usually you have one index. Here you can have multiple indices, and in addition to that, there can be indices on the top here or on the bottom here. Anyway, when you have tensors like this which have the same indices, then you can combine them to make one tensor with the same indices. So that's one thing you can do. Then when you do a tensor product between two tensors like this, well, all you have to do is to add those indices like this. And then when one of the indices here is the same, in the up part and the bottom part here, in the down part, well, you can simplify and remove that index. And finally, that's how we can get something like this, which actually are the Einstein field equations for gravity, for general relativity, in fact. And this looks, relatively simple, but in fact, there's a lot of things hidden behind that, as we will see. But the good news is that this particular equation, which again describes general relativity rules, is valid in all frames of reference. That's fantastic, because that this will work for any frame of reference you use, from anywhere, and will explain gravity and the courses of the planets and the galaxies and everything. So that's fantastic. Black holes, all this type of jazz. Okay. Now, before we go further, I want to talk about the special tensor. It's called the metric tensor. So in order to measure things, as you remember, we define things by measuring them. You remember the physical world and the mathematical world, the isomorphism between the two. Well, here, the metric tensor will help us to really measure things. For instance, this is a metric tensor. Because with it we can, define a shape, like this is, for instance, in this case, this is just a straight line like this. And we can also define units. You probably don't see them here, but there are units here. And you can change unit, then you change your metric tensor, and you can change the shape. So you don't necessarily have a straight line like this, to measure things. Sometimes you have to use curved metric tensors, to describe what's really going on, depending on, well, what's around you, if there's energy or if there is a mass. Okay, so this ruler here is really the metric tensor that we're going to talk about, and it actually describes the space-time we live in. So we're not only measure here space like we did with this ruler, but we also measure time at the same time, if I could say so. So we actually measure space-time with this type of rulers. So this is a bit complex, but it's very powerful. And it allows to measure space and time. Therefore, to be more correct, it measures space-time distances. Okay. I won't go to the details, but if you want to, again, you can go watch my other series of videos with all the math to explain that. And finally, just one comment. to make it a little bit more complicated, actually, the metric tensor can vary from point to point. In other words, you won't use the same metric tensor depending on the position where you are measuring things. And when I say position, I mean a position in space-time. Okay? And therefore, it's not just one metric tensor, but it's actually a field of metric tensors. But in any case, what you have to remember is that this specific tensor will allow us to describe how space-time is curved, or how we measure things in this space-time that we live in. Okay, that's a key point. Now, let's go back to this equation here. Okay, so as I said, it's Einstein's equation, and again, we'll see we can derive it, but we need mathematics for that. And we can derive it by merely, well, when I say merely, I think it's Susskind who said, every time I talk about general relativity, I gave a lecture, I say, okay, well, I should derive it from the thrifty universe principle, the principle of least action. And so he starts to do the derivation, and after 2 hours, he quit, and it probably takes a couple days, if you want to go through the full description. But in the math videos that I did, I explained all the steps that we need to go through in order to derive that from the TUP. But the important point is that from a simple principle like the TUP here, we can derive Einstein's field equations of general relativity, which explain so many things, in particular gravity. Now, how do we derive that? I'll just tell you the result. Well, we'll show that the variation of actions to determine the trajectory of a particle will look like something like this. And what happens is when you make this particular equation here equal to, or formula here equal to 0, then it becomes this, the field equations by Einstein. So it can be derived just using the thrifty universe principle. Now, in order, I just don't want to tell you, well, okay, this is the equation and we're done. No, I want to explain to you very quickly what it means, because that's the goal of this video. Well, these two tensors here, as you can guess, R and R mu nu, are two tensors, and they can be derived from a more complex tensor, which is called the Riemann tensor, and which looks like this. This one has 4 indices, but you can derive those two from it. And this particular tensor, the Riemann tensor, has all the information possible about how curved the space is, the space-time is. And it has really all the information. And those two are derived from it. Again, if you want more details, go see the math-oriented videos that I did. Now, the first one, mu nu, here, is called the Ricci tensor. And, intuitively, it corresponds to the growth rate of the space-time volumes. Okay, so you're at a point somewhere in space-time, and the Ricci tensor will tell you how fast, as soon as you go away from that point in space-time, how fast the volume will change, and will be curved, because it will depend on each and every position. This one is a scalar, basically a number, and as you know, it's also a tensor. And so this corresponds to the volume around a given point of space-time, again, but relative to what it would be in a flat space-time, where there's no mass, there's no energy, there's nothing, basically a flat space, like when you're in space and you let something, go like this at, constant translation speed. And so what that means is that it will tell you the ratio between the space-time where you are and a flat space-time, okay, for a given position in space-time. Now, the G mu nu here is a metric tensor. That's what will allow us, well, with the help of those numbers, to really measure things in this particular space-time, which can be curved, thanks to the R mu nu and R tensors. Okay, now what's on the right side of this equation? Well, I guess, h, you know what it is. It's number. It's easy. Pi, you probably know what it is as well. G is just a constant. It's a so-called, gravitation constant. Let's call it that way. And again, we have a tensor here. So what is this T mu nu tensor? Well, this T mu nu tensor is called the energy momentum tensor. And basically what information it contains is just all the densities and flows of energy which are given in a space-time volume. Again, all of this happens in a given volume. And so the T mu nu is a tensor which has all the information about what happens. And in particular, if you have mass in this particular volume, since mass is equal or equivalent to energy, well, it will have some impact here. So what that means is that if you change something here, so if the energy tensor here changes, or if, for instance, if mass, there is some mass here changing, well, it will be equal to a different value, of course, here, which means these tensors will change. And therefore, that means that mass and energy will transform and curve the space-time geometry, which is defined by those tensors, by this formula here with tensors. Okay, and this rule will be true for every frame of reference again, even non-Galilean frames of reference. And this is absolutely fantastic, So I hope, I've given you an idea of what's going on and what we mean when we say that, space-time geometry is curved by mass and energy. Okay. Again, if you want more details, I'll put a link in the description with more mathematics and where we'll be able to explain more thoroughly what's really going on. So much fun. Okay, take care. Bye-bye.